All right, let's talk about polyatomic ions. If you've ever found yourself staring at a huge list of them, thinking there has to be a better way than just memorizing all of this, well, you're in exactly the right place. Today, we're going to crack the code. I mean, just look at this thing: sulfate, nitrate, carbonate, ammonium. The list just goes on and on, right? It's one of the biggest hurdles in chemistry, and let's be honest, trying to cram all this into your brain feels, well, it's overwhelming. And it's not a very smart way to learn either. But what if we think about this a different way? What if this isn't a memorization problem at all? It's a strategy problem. You see, the issue isn't your memory. It's that nobody's handed you the right tools to solve the puzzle. And that's exactly what we're going to fix right now.
Two or more atoms bonded together carrying a charge. These act as a single ion.
Okay, let's dive right in with our first major shortcut. We're calling this the even/odd rule. And trust me, it's a fantastically simple trick for figuring out the charge on any polyatomic ion that's made of just two different elements. So here's how simple this is. You just look at the group numbers for the two atoms. If both of them are in an even numbered group, the charge is going to be -2. If you've got one even and one odd, the charge is -1. And for that one special case where both are odd, the charge is +1. That's it, seriously.
All right, theory is one thing, but let's see how this actually plays out with some real examples. This is where you're going to see just how powerful and how much of a time saver this little trick really is.
So let's start with a classic, sulfate. Okay, find sulfur on the periodic table. It's in group 6. And oxygen, same deal, group 6. So we have an even number plus an even number. And what does our rules say? Even plus even gives us a charge of -2, and look at that, it's exactly right. Sulfate is SO4 2 negative, no memorizing needed. And hey, while we're talking about sulfates, here's a little bonus tip for you. You've probably seen sulfate and sulfite. Well, the 8 version always has one more oxygen than the ite version. But here's the best part. The charge stays the same. So since sulfate is -2, sulfite is also -2. It's like a 2-for-1 deal. Okay, next up, nitrate. Nitrogen is in group 5. That's an odd number. Oxygen, we already know, is in group 6, an even number. So according to our rule, an odd plus an even should give us a charge of -1. And boom, nitrate is NO3-. See? It just works. And this isn't just for a couple of ions either. What about carbonate? Carbon's in group 4, oxygen's in group 6, both even, so you know it's a -2 charge. Or chlorate. Chlorine, group 7, that's odd. Oxygen, group 6, even, that gives us a -1 charge. It just keeps working again and again. All right, it's your turn. Let's put you in the driver's seat. Here's ammonium, NH4+. Go ahead and pause for a second, find nitrogen and hydrogen on the periodic table, and see if you can predict the charge using our even-odd rule. So, how'd you do? Let's break it down. Nitrogen's in group 5, which is an odd number. Hydrogen's in group 1, also an odd number. And what does our rule say for odd plus odd? A charge of +1. Ammonium is pretty much the only common positive polyatomic ion, and our rule nailed it perfectly. Now, this trick is incredibly useful, but it's not magic. Like any good shortcut, there are a couple of key exceptions you do still need to know. The big ones are phosphate and phosphite. Both of these guys have a -3 charge, which our rule isn't going to predict. So just go ahead and lock those two.
We'll start with sulfate and nitrate here. Next, we have carbonate and ammonium. Notice how the charges glow, indicating their reactivity.
Thinking, okay, this is great, but what about those more complicated ions? And that's a really good question. The even-odd rule is perfect for ions with two different elements, but sometimes, we run into ones with more. For example, take a look at hydrogen sulfate. You've got hydrogen, sulfur, and oxygen all in one package. Our first trick doesn't have a rule for 3 different elements. So do we have to go back to memorizing? No way, absolutely not. We just need a different tool. And that brings us to our second trick, the building block method. The idea here is to stop seeing these complex ions as one big, scary molecule, and instead see them as smaller, familiar pieces that are just stuck together. It's really simple.
First, you just find the polyatomic ion you already know inside the bigger one. Then you just add its charge to the charge of the other piece, which is usually a simple ion like hydrogen. It's just basic addition. Let's try it with hydrogen sulfate. Look closely. Do you see a familiar piece in there? Yep, right there. SO4 is just the sulfate ion, and we already know that has a -2 charge. The other piece is hydrogen, H, which we know likes to form a +1 ion. And now for the easy part. We just add those charges up. You've got a +1 from the hydrogen plus a -2 from the sulfate, which gives us a grand total of -1. So the charge on the hydrogen sulfate ion is -1. Simple. And this isn't a one-hit wonder either. This method works all over the place. Look at hydrogen carbonate. That's a +1 hydrogen and a -2 carbonate. Adds up to -1. Or how about dihydrogen phosphate? That's 2 hydrogens, so that's a +2 total, plus our exception, phosphate, at -3. +2 plus -3, also -1. It's a system that just works. So there you have it. 2 really powerful tricks. You've got the even/odd rule for the 2-element ions and the building block method for the more complex ones. This isn't just a random collection of tips. This is a brand new toolkit for how you approach these kinds of chemistry problems. I mean, think about the shift here. You're no longer just passively trying to memorize a list of facts. You're now an active problem solver. You can look at an ion you've never seen before, break it down using logic and the periodic table, and literally decode it like it's a puzzle. And that is a
Notice here, the sulfate ion SO4 remains together. The ammonium ion NHF also stays intact. Polyatomic ions remain intact during reactions.
Later.